Before I could continue with the computer logic series, moving on to what might be called clocked logic or sequential logic. In other words, logic that doesn't just allow the inputs to settle and read the outputs, but rather logic that moves in a sequence from one thing to another to another to another in usually synchronized with a clock signal, which we will talk about. But before I could get there, what I wanted to do was to build this box that you see here in front of you. It's a rather simple, actually it's two circuits, that both of them are identical, and they're shown down here below. Let me show you first just the one circuit. This is a circuit built of NAND gates, and I call it circuit A. This is a NAND gate, a 74LS100. This is two of the gates in a package. There are four in a package. And it's interconnected in a way where the outputs are connected back to the inputs. And then you see over on the left here is a switch that we can turn so that this input is grounded or this input is grounded. This is a simple form of storage that will store the previous position of this switch. In other words, if I switch the switch and then I remove the switch entirely, this gate or this cross-connected set of two NAND gates will retain the state. And let's talk about that in just in the next segment. For now, don't worry about the capacitors, the resistors, and these 74LS14s. We'll talk about those a little bit later. Just focus on this circuit. If you remember, a NAND gate's output is a 1 when any of its inputs are a 0. So, if we have the switch in this position, this gate will be a 0 on pin 1. That will force a 1, a logic 1 on pin 3. Because pin 5 is floating, it's also a 1. Remember I said in part, the first combinational part of this series, you shouldn't normally leave these floating. But in this case, it's not a serious problem because I know this switch is always going to be either in this position or in this position. And this 1, combined with this 1 on 5, floating 1, produces a 0 on 6. The 0 on 6 then produces a 0 on 2, which reinforces the 1 on 3. Now, if I were to cut the switch at this point, that gate would remain that way as long as we kept power applied to it. In other words, it will latch. It's like the switch in your room that turns on the light. It can be in one position or it can be in the other position. So you might ask, well, how is that different from this switch? Well, the difference is that one thing you will find about logic is it responds very quickly to signals. And unfortunately, mechanical devices like switches are not perfect. When you switch a switch, it bounces. And as it bounces, if you think about it, it's like the switch was bouncing back and forth from this side to this side to this side to this side, and then it finally settles down in this position. But while it's doing that, if you had a logic circuit out there that was just tied to these points, it would see all those bounces. And we may look at that at some point a little bit later. But right now, the point of this latch is to respond to the very first time that a 0 is applied to this input. In other words, when the switch first touches that contact, for a fraction of a second, in fact for only a few nanoseconds, this gate will immediately go to a 1. This gate will, I say immediately, within a few nanoseconds, this gate will go to a 1. This gate will, within a few more nanoseconds, go to a 0. And once it does, this latch is set. Doesn't matter if the switch keeps bouncing. So, this circuit is sometimes called a latch. It's sometimes called a debouncer. It's sometimes called an RS flip-flop. Now, what does that all mean? Well, we're about to move into the world of flip-flops. And this is a simple reset-set flip-flop. In other words, when the switch is down, this gate resets. When the switch is turned up, this gate sets. And so it's a reset-set flip-flop, or RS flip-flop. So let's take a look at how that looks up here. I have arranged a pair of LEDs that you see at the top. So as I switch this switch, you see the LED comes on, showing that this signal, that is this switch, which is also connected to a second circuit. Remember we talked about that circuit. Well, there's a duplicate down here that I call B. Let's, for now, it doesn't matter how we call these, but for now let's call the one on the right B and the one on the left A. So as you see, B is set, A is set, B is reset, A is reset. A can be set or reset independently of B. And the reason I constructed this circuit and put it in this nice convenient box and arranged for the outputs and so on was to not only to illustrate how a set reset flip-flop works, or a latch or a switch debouncer, but also as a source of signals that we can use in some of our experiments later with sequential logic. So now let me talk about the second part of this circuit. As you notice, this output is connected through a capacitor. A capacitor only passes changes. So a signal passes through this capacitor whenever this point changes. And it's applied to this inverter gate. And this is really just a buffer. Based on this changing, this will change as well. But it will only change for the length of time it takes for the capacitor to discharge through this 330 ohm resistor. In other words, when this goes from a 0 to a 1, the capacitor is charged with essentially a 0 on this side and a 1 on this side. That then starts applying current through that 330 ohm resistor, which raises the input of this gate to a 1. But as the capacitor discharges, this voltage will go down. Eventually it'll get down to a 0. And at that point, the input of this will be a 0. In other words, it goes to a 1 for a little while and then comes back to a 0. That is then inverted. And we call that the A minus signal because it's a negative going pulse. It's a positive going pulse here, then it's inverted to become a negative going pulse. Similarly, the one below does the reverse. In other words, it triggers when this switches, the capacitor couples that, the inverter inverts it, and we get a positive going pulse. So let's take a look at that on the scope. Here is an oscilloscope set up and connected by this probe to the positive plus output, which is this output. In other words, the A plus output. The scope is set for single trigger. Don't worry about that right now. I'm now going to switch A first on and then off. And you'll notice that we got a positive pulse on the oscilloscope. Once again, you don't need to understand how to use an oscilloscope yet. We'll talk about that a little bit toward the end of this course. But what is happening here is, if you think of this as time, in other words, a clock that's ticking along, and each tick is one space, so tick, 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 tick. And this direction is the voltage. We're only interested in ones and zeros. This is a 0 level, this is a 0 level, and up here is a 1 level. So this signal ticks along at a 0, tick, 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 until it gets to here. Then it jumps to a 1, tick, tick, and part of a tick, and then it goes back to a 0 again. That is what the circuit on the right does for us. Now we'll use both of these circuits in working with various sequential logic gates, including flip-flops. Remember, this is an RS flip-flop. There are a bunch of other kinds. And clocks. We're going to be using pulses like this and this as clocks. If it's A plus, that's a positive clock. In other words, it clocks when it goes positive. The A minus is in case we need a clock that goes negative. At this point, we're going to stop looking at this RS flip-flop with these capacitor-coupled pulse generators. And in the next segment, we'll talk about other kinds of flip-flops besides the RS flip-flop. So, once again, B, A, not A, not B. I hope you enjoyed this segment, and I hope you'll stay tuned to the next part on sequential logic.